So for the fourth question, we are going to go through an equation on a series DC motor. And we know that for a series DC motor, it's a different construction. You will have a series winding connected together with the field circuit and the armature circuit. We will have the circuit looking like this. Okay, you will have EA, and then RA, and then RS, and then LS, and then the terminal voltage. Okay, connected like this. So when there is a DC current, so basically this will just become a short circuit, alright? But when there is an armature reaction, obviously we have to take into account this conductor, okay? This inductor, sorry. Okay, so in this case, the series motor has a field winding of 33 turns per pole. Okay, so these have an S of 33 turns per pole, and then the rated voltage is 240 volts, rated current 76 ampere, and its rated speed at 600 rpm. Okay, so it has armature resistance of 0.09 ohm, and the field resistance is 0.06 ohm. Okay, so the magnetization curve is actually expressed in terms of a table there. Okay, this has actually come up in a midterm before, and there is a lot that a lot of people are taken by surprise, because we are used to looking at magnetization curve that looks like a curve. So when it is tabulated, you are somehow, I'm not sure, don't know how to plot. Or the good way of doing this is basically, if you are stuck, it's better for you to plot. Okay, so it is the force versus EA. So obviously EA is here, and you have MMF F here, right? You will have, for example, 500. Okay, so you have 95, 150, 188, 212, and 229, and 243. And then you will have 500, 1000, 1500, 2000, and 2500, and 3000. So it will probably look like this. Okay, all right, so this would be your plot lah. Okay, but since you have it tabulated like this, you will need to do a linear interpolation. So I know when we talk about linear interpolations, okay, I forgot the equation and whatsoever. It is important to know that with linear interpolation, we are making the assumption that between the point that you want to know and the range that you already know, it shares the same slope. Okay, so as long as you can find the slope, you can equate that into your equation. Okay, so in this case, for example, it asks for a motor torque, speed, and output power at 33%, 67%, 100%, and 133% of full load armature current. Okay, so we know that full load current here, okay, is a rated load lah, in this case, right, at 76 ampere. Okay, so if 33%, this would mean 33 per 100 times 76 ampere, which is 25.3 ampere. So at what else, 67%, it is 50.7 ampere. At 100%, it is 76, obviously. And then at 133%, it is 101.3 ampere. And this is the amount of armature current, okay, at different percentage of full load current. So if IA is 25.3 ampere, we know that the internal generated voltage would be VT minus IA. Since it is a series, so we must add the series resistance as well. So 240 volts minus 25.3 times 0.09 plus 0.06 ohm. Okay, so this is 236.2 volts. Okay, now we know that to know the speed of this motor, we want to be able to use the magnetization curve lah. Okay, since the magnetization curve is given at 900 rpm, we need to find out the EA lah. Okay, the EA that we have for this. Okay, by knowing the magnetomotive force that we have inside this machine. Okay, so the magnetomotive force is obviously NI or NIA. Okay, so the number of turns is 33 turns. Okay, and IA is 25.3 ampere, so we will have 835 ampere turns. Okay, so if we have 835 ampere turns, if we take a look at this table, we know that it is between 500 and 1000. Okay, so typically what we do is we use linear interpolation equation. Okay, so linear interpolation equation is, okay, you can Google actually this, but you can also use the assumption that the slope between this point, okay, these 2 points is actually linear. So what we can have is we will first try to find the slope, which is by getting the two variables, or the first and the second variable, the first and the second set of values from the table. Okay, so M is actually y2 minus y1 over x2 minus x1. So y2 here is the F, so 1000 minus 500 divided by x2 minus x1, 150 minus 95. Okay, so it will be 500 divided by 55, right? Okay, so that will give you the slope lah, which is 9.09. Okay, so the C is simply y equals to mx plus c, right? So the C is, we take any of the pair. So say if I take 100 and 150, so it's 1000 minus 9 equals to 9.09 times 150 plus C, and this C will give you 363. So C is minus 363. Okay, 0.6. Okay, so the equation is actually y equals to 9.09x minus 363.6. Okay, so if you want to know how much, so y here refers to the magnetomotive force. Okay, and EA, X is EA, so Y refers to magnetomotive force and X is EA. Okay, so if we want to know how much is EA, we simply rearrange the equation, Y plus 363.6 divided by 9.09, okay, times EA, or times X here. Okay, so the magnetomotive force that we calculate is 835 plus 363.6 divided by 9.09, sorry, not times x, 9.09. Okay, so this will give you the value lah, okay, or the answer, which is 134 volts. Okay, so this 134 volts is attained at 900 RPM, because the graph is actually, or the value that we have is actually taken from when the motor is running at 900 RPM. Okay, so right now we already know that we have some internal generated voltage at some speed, and we also know that the internal generated voltage with that amount of current is actually 236.2. So we want to know what kind of speed that we're talking about. So it's EA at 23.3 divided by speed at 23.3 that we don't know yet. And then we have EA that we just calculated divided by the speed. So EA from the curve, okay, and the speed from the curve. So EA at 23.3 is 236 volts divided by speed that we wanted to know. And then the EA from the curve is 134 volts. You divide by the speed. Okay, so the speed here is 900 RPM. Okay, so this will give you 1586 RPM. Okay, so this concludes the speed.